screen.
Hmm?
It's visible in full screen.
Can you see it on full screen?
Yes. Yes.
Okay. Yeah.
Welcome to all the delegates for the memorial talk 1. This is the memory of Professor Amitabha Bhattacharyya. This lecture will be delivered by Dr. N. Ramesh Babu, Balram Institute Chair, Professor, Manufacturing Section, IIT Madras, Chennai. His topic is on a framework for design and development of high precision cylindrical grinding machines. Now we request Sri P.J. Mohan Ram, Senior Advisor, Indian Mission Tool Association, to chair the session with their hand in. Thank you.
Thank you, Professor Babu. Friends, it gives me great pleasure to be here to listen to Dr. Ramesh Babu from IIT Madras on the important subject that he is going to speak on. To give a brief introduction, this is the Amitabha Bhattacharyya Memorial Lecture, which is delivered at every Aimtdr conference. And to those of you who are not very well versed, Dr. Amitabha Bhattacharyya is a pioneer in the field of machine tools in India. The efforts and contributions of Professor Bhattacharya in the field of machine tools and advanced manufacturing processes and technologies is during his professional journey of about 3 to 4 decades. And he is to Indian machine tool industry what Professor Koenigsberger was to the British machine tool industry. So, in memory of his contributions, this lecture presents the efforts made towards building a framework for developing high-precision machine tools in India. I would now like to introduce Professor Ramesh Babu from IIT Madras, who is the speaker today morning, delivering the Amitabha Bhattacharya Memorial Lecture. Professor Ramesh Babu is currently serving as the B. Balraman Institute Chair Professor, the Department of Mechanical Engineering at the Indian Institute of Technology, Madras. He holds an additional responsibility of Secretary, Advanced Manufacturing Technology Development Center, which is engaged in the development of advanced machine tools and manufacturing technologies through industry-academia partnership at the IIT Madras Research Park. Professor Ramesh Babu has more than 3 decades of experience in the field of manufacturing, with an expertise in advanced machining processes, automation and robotics in manufacturing, precision machine tools, and smart manufacturing. He is also an honorary professor at the College of Engineering, University of Swansea, UK, member of an external advisory board of Center of Innovation in Mechanics for Design and Manufacturing, Texas A&M Engineering Experiment Station, USA. He has published more than 200 research articles in reputed journals and conferences, the guidance of 25 doctoral students. He has organized 5 international conferences. He has organized 5 international conferences, including 2 Aimtdr conferences and several national conferences for the advancement of manufacturing technology and robotics in India. I would also like to add that he runs a very advanced sheet metal forming facility at the IIT Madras, which came out as a result of his association with the Yamada Company of Japan. And he is very well known in circles as a person who works very closely with industry in developing new technologies and technological capabilities. His group at the AMTDC Madras has developed 11 research projects along with the machine tool industry, which was funded and piloted by the Department of Heavy Engineering, the Ministry of Heavy Engineering, the Ministry of Heavy Industries, New Delhi. The present lecture that he is going to deliver is on one such project, which was sponsored by the PSA's office, which is on the framework for design and development of high-precision cylindrical grinding machine. So I would now hand over the mic to Professor Ramesh Babu to take us through his presentation. Professor Ramesh Babu.
Yeah. Thank you, Mr. Mohan Ram. Can you hear me?
Yes, we can hear you. Yes.
Yeah, thank you very much. I'm really honored to have you as the chairman of this particular session. I just wanted to briefly say a few things before I go into the talk, which I'm going to deliver it in the next few minutes. So at the outset, I express my gratitude to the organizers of Aimtdr conference for having invited me to deliver the Professor Amitabha Bhattacharyya Memorial Lecture at the conference being organized by PSG institutions. I consider it a great privilege and thank all my colleagues for bestowing this honor on me. And according to me, the memorial lecture should really try to extrapolate to the extent possible what Professor Bhattacharya would have said had he been with us today. So I had known Professor Bhattacharya as an eminent teacher and a distinguished researcher in the field of machine tools and production engineering. I happened to see him only once at Aimtdr conference in 1988, held at Jadavpur University. I have come to know that he had a vast experience in a wide spectrum of activities, ranging from engineering education, research, through planning and developmental work, even to administration and management. His research efforts in metal cutting and machine tools are very well known through the textbooks on metal cutting, theory and practice, and principles of machine tools. And these books are still being considered as one of the best and are read by the undergraduate and postgraduate students. And Professor Bhattacharya made outstanding contributions to industrial and professional research, but also developed the robotics lab in 1980s itself at Jadavpur University to encourage teaching and research in robotics, CAD/CAM, FMS, etc. So further, he was also instrumental in developing an advanced laboratories of unconventional machining processes even those days at Jadavpur University, and guided a number of doctoral students in these areas. His school of teaching offered learners the chance to apply the fundamental concepts and analytical abilities and supplied the spark needed for effective teaching and research programs in the course of time. He was a staunch advocate for the development of technologies indigenously. And I recall one incident when we submitted a proposal to the DST in 1990s on the applications of abrasive water jet technology in manufacturing, wherein he said that we should develop these technologies indigenously rather than importing these technologies. I think he was the chairman of the PSC at that time. So having known the philosophy of teaching and research, I have chosen to deliver this particular lecture on the framework for the design and development of high precision grinding machine tools. And this is chosen in view of the theme of the conference being transformational changes in manufacturing. And by virtue of my involvement in many Aimtdr conferences, I know the audience being both from academia and industry. And in this particular lecture, I try to be more specific and direct to fulfill the theme of the conference and also needs of the audience who are listening to me. Thank you. I think this particular slide illustrates the Professor Amitabha Bhattacharya's profile, which I have collected it from some report which I could get it. So I think I just give an outline of my presentations, and today's presentation in the next 40-45 minutes. I would like to give a status of developing such technologies which are known as the mother technologies and mother machine tools. And based on the report brought out by the IMTMA in 2020-21, I think that is the basis on which I just wanted to start my intro. And then I think there are several other reports which were made available to us in the open domain. Okay, one can easily look at them also. I'll just briefly touch upon those things. And also the efforts of many experts, whom we have seen today as the Lifetime Achievement Awardees. I think they have also contributed immensely to bring out those reports and roadmap for the machine tool sector. And then I will get into the project on which I have worked for almost 5 years to develop the framework for characterizing the machine tool, and then use the same framework for developing it as developing this machine into a high precision machine tool. I think this has actually taken us to the level of transferring the technology, and it was actually funded by the Principal Scientific Advisor's Office with the team advising us and monitoring the activities from time to time. I think at the end of this, I would also briefly talk about the transformational change we have brought in by means of setting up an advanced manufacturing technology development center at IITM Research Park as a separate entity. And I will just briefly tell about it to bring the advances and changes that we have been making it in this particular area. I think this report, I have taken it from the IMTMA annual report, wherein they have clearly brought out the level of dependence on the imported technologies. And these technologies are needed for building the machines of different grades, right from the normal production grade that is being used routinely in the job shops and many workshops to a precision and high precision machines. So in all these machines, what we need is certain technologies which are known as the mother technologies. I think they range from the electrical, mechanical, and electromechanical and hydraulic, etc. So I'm not getting into the details of them. But then as you can see that the red color indicates the technologies being imported, and the green color actually indicates the efforts that are going on over the last few decades, both by the industry as well as the academia. And the right side slide shows the imports of for bringing all these technologies and developing these machines, and the exports are very, very limited. So what it clearly brings out is that we need to really look at the way that these technologies are made available in this country to make these machine tools affordable by many, right from the low end to the high end machines. I think this is the just basis. And then, of course, if you go and look at some of the reports which are available and which are brought out by the Planning Commission under the 12th Five Plan itself, they have stressed the need to increase the depth in the technology by way of industry-academia collaboration. In the sense, unless the academia looks at the problems of the industry and then intensely takes it forward, so we will not be able to really build this sort of a supply chain that can look at the design to the manufacturing and finally assembly and technology transfer. I think that's where I think the efforts are going on at the moment, and some of the efforts have also been brought out in the technology roadmap, wherein they have clearly identified several technologies which need to be developed in this country. And I think I'm not getting into those details. I think for those of you who are interested can easily look at this technology roadmap, which was brought out by the PAC, which was steered by the members like Mr. Mohan Ram and Professor Mehta and others. So one of the points here is the encourage academia industry R&D collaboration for building the machines of the next generation, wherein the productivity is extremely important apart from the precision, reliability, etc. I think so. You will see that this particular presentation which I am making falls into one of those categories of building the high precision machine tools. I think the machine tools require the machines of higher precision as the norms for the environmental pollution and even the efficiency, etc., have changed from time to time. I think it is clear from this particular slide that in every industry you need the tolerances which range from a few microns to the few hundreds of nanometers, etc. I think this is where our project, which was funded by the Principal Scientific Advisor's Office, considered the requirements of the industry first before we actually made the requirements for building this machine. I think we had a detailed survey and visit to various industries, and these industries have clearly given the requirements in terms of various parameters that are indicated here in this particular table, and that has shown that we need to build these machines of the next generation with the current capabilities available in this country with the machine tool builders, etc. So that has really made us to think of a grinder that need to be either upgraded or modified into a next generation precision grinder. I think this was done in a collaborative mode with the industry, academia, associations, and various other stakeholders who use these machines also. I think that's where you can see the set of specifications which are known as the targeted specifications are listed out in this particular table. As you can see, the roundness and the concentricity are far lower than what we have been producing it in 2010-11. I think this was a project of almost 4 to 5 years duration to interact with many industry partners and also many stakeholders who have tested these machines and proved these concepts also. I think that's where the CMTI, the AIMTDF also has played an important role to support this activity. I think when we started, we were not very clear of what we have to do it and how we have to proceed. But then the industry partner, Micromatic Grinding Technologies, was kind enough to give us all the details which they have it in building the machine. And our team has worked with their team very closely and then brought out this anatomy as a building block, which can be used for subsequent projects also. The other one is, as you can see, that I'm not getting into the details of each and every module for the reason that, and most of the people who are familiar with these machine tools, they know that the machine tool requires a bed, and over that you have a table and carriage, and then on the top of it you have a wheel spindle head, and then the work head and tail stock, of course the tooling, etc. So if that is the basis for making a machine tool, I think each and every unit of this machine is extremely important if you want to really build the precision machine of the order that we have stated in the previous slide. So I think we felt that unless we characterize the existing machine and find out the weaknesses in the existing machine, and then benchmark it with some machine, which is the precision machine giving out the specifications, that are indicated in the table of my previous slide. So we felt that I think we need to bring that sort of an approach if you wanted to really build the next generation machines. So I think what you see here is the efforts that have gone into it in order to characterize this machine. As you see that the grinding is a very complex process, and there are so many inputs in order to realize certain outputs on the parts, which need to be very precise. And of course, this particular machine is a cylindrical grinding machine, wherein the tool and work interaction is extremely crucial if you wanted to really make the system into a very precise and robust one. So I think what you can see in this, maybe I can just use the pointer to bring out some of them. Yeah, so as you see that you can find out, you can see the various inputs such as the mechanical system plus the tooling, and of course various other parameters such as the grinding and dressing parameters. All of them influence the quality of the part produced by the machine. And as far as the machine tool is concerned, it has its own anatomy, as I have mentioned it in the previous slide. But then this anatomy has to be made into a robust one if you have to really achieve the accuracies of the order that we needed for the high precision machine tool. And as you can see that now we need to consider all the aspects such as the kinematics as well as the dynamics of the machine. And while we are dealing with the dynamics, we have to look at both mechanical dynamics as well as the thermal dynamics. And of course, the process capability and stability of the process is also equally important. So hence, as you can see that the transformation that we need to bring in the existing machines to make them into modern machines or high precision machines requires an in-depth study of all these interactions among the various components. So that has really made us to think about the characterization of the entire machine tool with various units being integrated to build this machine tool. So I think that's where we have extensively performed the tests to characterize these machines, and these tests are the experimental tests are some of them, and even we have used the analytical methods also to build several models which can eventually help us to use it in the reverse mode or in the inverse mode, so that the suggestions can be given to build a next generation precision machine. So I think what I have listed out here is nothing but the vast amount of work that has gone into it in evaluating the performance of various units of a machine tool. And of course, at the end, we need to look at the overall capability of this machine also. And this required a lot of effort from various industries, various testing organizations like Advanced Machine Tool Testing Facility, and then internal capabilities and academic inputs, etc. So that's where you can see it's a complex nature of the interaction in order to bring out this sort of a framework. I think this framework not only helped us to characterize and identify the weaknesses, but also helped us to use this framework for developing the next generation machine. I think I'm just going to present some of these thoughts and some of these efforts in the next few slides. So I think if you just look at it as the black box, you will see that there are certain inputs and there are certain outputs which we expected from a machine of a high precision in nature. And of course, inside this black box, you will see this process that is happening between the workpiece and then cutting tool. And this interaction is captured by way of 4 blocks, like a geometric accuracy. What will be the volumetric accuracy of this machine in the work volume? And then what is its mechanical and thermal stability or a thermal rigidity? I think these are the aspects which are seen to be extremely important if you wanted to transform this one into a next generation machine. I think that's where the extensive study and analysis was made on the machine with only 2 axes. But then it has, as you see these from bottom, if you look at the bed, then you have a table assembly, then carriage assembly, then wheel head assembly, then workhead assembly. And these are the assemblies which again use several components. And each and every component also has to be machined very precisely. And then we need to follow certain assembly practices if you have to produce those units in a very precise manner. I think hence now the information that I have provided here is basically to find out the volumetric error in the work volume, and that required both geometric as well as the kinematic measurements. In the sense, what is the error in the geometric, both positioning, angular positioning, etc. Whereas in kinematics means how the various units are assembled to bring out the parallelism and also the perpendicularity. I think that required various measurements using the laser interferometers and other instrumentation, and that will only give you an accuracy in the static. But then when you're operating this machine, and depending on the conditions and depending on the material removal rates, etc. So both the static as well as the dynamic rigidity or a compliance of this machine also plays a vital role in affecting the precision. I think I'll also show you at the end that what is the role of each of them in producing the accurate machine tool. I think the another important aspect which we normally ignore it when we are operating this machine is the thermal behavior. I think we have found out that the thermal behavior of the machine is extremely crucial for maintaining the precision on the components. I think that has resulted into a biggest contributor in making the machine tools into precise machine tools. I think what I have listed out here is the entire the story of how we can really assess the thermal behavior of the machine tool by thermal imaging and identifying the hot spots and carrying out some measures to pull those areas, etc. And then of course the spindle and the axis are the ones which are actually moving the work and moving the tool. So hence the spindle growth is also very important to measure and then compensate for. I think that's where a lot of work has gone into it through a series of studies and efforts. And I think these are the various aspects that one need to consider if you have to really make a machine of a high precision in nature. I think I just wanted to give you a flavor of what we have done it, how we have identified the weaknesses of the existing machine. I think this data is related to the existing grinding machine being produced by the machine tool builder in 2000 10 and 2011, 12. So we found out that the positioning accuracy itself is seen to be about 16 microns over 300 millimeters. But then we are aiming to build a machine with less than 3 microns, less than 5 microns. I think you can easily imagine that these accuracies are not going to really produce a high precision components on this machine. So hence we just took this information and attempted to build this sort of a model, and which is helpful for us to do some sensitivity analysis and identify the root causes for the inaccuracies, and also same thing will also help us to improve those areas where the precision as well as the accuracies can be enhanced. So I think that is one side. Then the other one is the thermal characterization. While we were characterizing this machine, we found out that no two results are similar. In the sense, we found that the drift of the spindle and the growth of the axis are the ones which are giving very different results from time to time. I think that really made us to look at it in a holistic way, and then seen the thermal characterizations as the most important and crucial in case of precision machining and precision machine tools. I think this is where one would notice that I think if you look at this sort of an error about 16 microns is the error. I think you can see the growth with respect to time, that it took almost 300 and odd minutes for the entire temperature on the wheel head to come to a stabilized mode. So I think T1, T2, T3, T4 are the points on the wheel head housing. And when we monitored the temperature, and at the same time we monitored the drift of the spindle also using the spindle the error analyzer. So we just found that in the existing machines it takes about 3 to 5 hours of course for the machine to get into stabilization. I think that's going to be too long, so we felt that we need to reduce these times also if you wanted to utilize these machines more usefully. I think the second one is the drift which I mentioned on the axis itself. So as you see, this is only a 2-axis machine. One is along the table and the other one is along the carriage. These 2 axes we monitored it, and we found out that the deviation is also quite high in case of the axis. So I think you can see that the temperature was maintained at 23 degrees centigrade, and in order to ensure that these deviations will be kept to minimum, but even with that, and you can see the measurement at the grinding zone increasing from, okay, this is a few microns of about 10 microns, 11 microns. So then we also saw that the wheel spindle head itself is driven indirectly by means of a belt drive. And that is the one which is also really causing this entire carriage and the other units to have this sort of a deformation. So I think the first two, like one is the volumetric accuracy, which used only the geometric as well as the kinematic error, gave us some information about the machine and its behavior. But then the thermal characterization has thrown more insights into how the machine is behaving, and due to the construction and the way the various units were placed on this one. So I think these are the insights which we got it by means of the study. But then we thought that in order to have a completeness for the project, so we also felt that the structural and the mechanical rigidity of the system also has to be assessed. So we did carry out certain tests, and some models were built in order to provide this as the base framework which can be used in the inverse mode to come up with some suggestions. Though the dynamic studies have not offered much, but then still it was useful for us to conclude that the machine base and the other units have enough rigidity for the machine to withstand all those loads and the speeds, etc. Now, of course, during this process, we did develop some models that have identified the manufacturing practices being followed by the machine tool builders in terms of the tolerances and the allowances that are provided on various components. I think some of the models are basically tolerance stack-up models and then tolerance synthesis models, which help us to allot the tolerances on different components of each assembly, such as the wheel spindle head assembly, and then work head, assemblies, etc. And at the same time, this model, which incorporated the various mechanical properties of the components and joints and the various units which are moving in relation to each other. I think that also gave us some confidence of how to really design the systems. I think the dynamic rigidity, as you can see that we did develop this sort of a finite element model to ensure that this model can help us in future. And at the same time, with the experimental model analysis, we have gathered the data about the machine and the machine structures, etc. I think this is by using the standard methods of using the hammer with accelerometer being placed at different locations. And we found out from this data, you can see the mode shapes at different frequencies. And normally the spindles are operated at about 3000 to 5000 RPM. The frequencies will be in the range of 50 to 80 hertz. So I think it's only a rigid body deformation without any bending or twisting, etc. So hence we concluded that this machine has a good rigidity as far as the mechanical properties are concerned. So I think this, the entire effort is basically to characterize this machine and identify the various areas that can be improved. So we did use the same approach to build several models and integrate them into a framework. And we brought them into different categories, such as the error model, wherein the volumetric accuracy is the main concern, and then stress model, where the static compliance and dynamic compliance of the machine is of utmost importance, and the thermal model that covered both the drift of the spindle and the axis, so to plan and implement those compensation strategies, etc. I think all these models have been utilized in order to come up with some suggestions for designing the next generation machine. As you can see that the violet one is nothing but the model that we have built it, and the green color ones is the one wherein we can really identify various terms that can really influence the units of the various assemblies. And of course, we can also identify the major components that can affect the volumetric accuracy through the sensitivity analysis. I think that's this particular model, which is known as the error model, can really help us to identify the areas of improvement. And that's where we have come up with some suggestions on the designing and assembly of various units. In a similar way, that we also use this data which we have collected from the existing machine, and we also utilized several analytical approaches in order to build these models and create this sort of a framework wherein you can see the role of contact surfaces in the stiffness of the various loops, which are known as the tool loop and work loop, and the combination is the one that will really produce a machine. So I think the red colored ones are the ones which aid us in suggesting certain things like how do we allocate the tolerances, and how do we really make the surfaces to be in contact with each other in a more rigid fashion. And so, and these are helpful for anybody to come up with some suggestions, and also the advice for the manufacturing professionals. So the last model is basically a thermal related model that utilize the data collected from the thermal mapping and thermal growth of the spindle and thermal deformation of the axis. And again, by means of utilizing these models, we have also suggested that the direct drive motor will really improve the thermal capability of this machine, and of course the controlling the ambient conditions during the operation of this machine also will bring down these errors to a significant level. So as you can see that this entire effort is essentially a combination of both experimental and analytical methods, which we don't normally do it while taking up any project. So we look at it only in the factor improvement methods we use it, and if we improve the stiffness or if we improve the thermal stability, etc., are seen in isolation. But then this particular project, which has dealt with all these components of both static as well as the dynamic aspects of this machine tool, has made us to build this particular framework, and that has also helped us to come up with the suggestions, and these suggestions were implemented, and we have also tested the machine after it has been fully built, and even the trials were carried out in an exhaustive way before the entire machine was proved to be a high precision machine. I think what I'm going to show you is some of the suggestions that we have come up. I think if you look at the diagram on the left hand side, about 75% of the errors are due to the thermal drift. This is only the spindle drift itself, but the axis positioning error is about 20%. But whereas the errors due to the other things such as the static and dynamic compliance of the machines and process related is very, very low. So thus this suggests that now we need to focus more on the thermal compensation aspects and over the other aspects, etc. So I think we also suggested certain changes in order to make these machines easily reproducible. Because one of the things we have noticed is if you use the V and flat guideways, the time taken for scraping and then making the alignments is going to take more time. So we felt that the linear motion guideways can really reduce the time for building this machine tool also. And of course, the ball screw pretensioning has reduced the deformations to a certain extent. And the direct drive spindle has also helped us to reduce the deformations caused to the overhanging of the entire the motor, which is driving the wheel head spindlets. So I think this is the machine that was inaugurated by the Dr. Chidambaram, who was the principal scientific advisor at that time. And I think we further evaluated the various parameters in order to bring out a comparison between the next generation precision grinder versus the existing grinder. And this table clearly shows that the axis positioning errors have been brought down from 16 microns to 1.9 microns. And similarly, of course, in both the axis and the backlash also was brought down to 0.2 microns. And the step response by using the sort of LEM guideways has also significantly improved it. So why I'm showing this one is in the sense, see, when we didn't have any data about how to build a machine tool, I think this approach that we have followed has really helped us to bring out the framework and to evaluate the capability of the machine, and of course the static as well as the dynamic stiffness of this machine also has improved substantially. I think what you see is between different components for each of those assemblies, such as the wheel spindle head, work head, etc. So I think this particular diagram actually shows the two aspects. I have put these arrows here, and if you look at this one, this is about like 7 to 16 microns is the error. And I think this is where you can see this 19 microns is the x-axis and z-axis about 26 microns. And this error in the axis can be brought down to 6 in the x direction and then 18 to z direction. I think this is the data that we have collected on the machine that we have improved. So the other few aspects which are indicated here are basically the stabilization period also has been brought down to only a maximum 1 hour. And earlier it used to take more than 3 to 4 hours. But then this is very, very important in order to utilize this machine more effectively. And we have made several changes in the spindle system by providing the cooling jackets and for it to stabilize quickly. And we have also used the direct drive instead of using the indirect drive for reducing the thermal deformations, etc. So as you can see that now this the linear axis, both the x-axis growth is shown here for the previous machine versus the new machine with the modifications. And this has also improved the tolerance grade substantially. I think those studies were carried out after the completion of the machine building and then using the tooling and fixturing for grinding different types of components taken from different industries. So I just wanted to give you some insights into the various trials that we have carried out on different components. And as you can see from this particular table that the achievable tolerance grades have been improved substantially with this machine having undergone several changes at various units. So I think what I wanted to convey here is this approach is basically an approach of characterization which has resulted into the development of several models. And these models are integrated in order to build this framework, which we call it as a characterization framework for assessing the capabilities of this machine to begin with. And the same thing can be used in the inverse mode as a developmental framework, which we have seen in some of the models, like what we can really deduce from these models. So hence, by way of characterizing and using these models, it is possible for us to come up with some suggestions, and even these suggestions were implemented by our partner and build this next generation machines. I think some of the changes have been made in spindle side and the structural interfaces. Some redesigning was attempted, and the geometric accuracies were also improved, and the drive systems were modified to a certain extent by using different types of elements such as the LM guideways and the ball screws with fine pitch and pre-tensioning, etc. So I think this is the machine. It's a collaborative effort. It is not the effort of one academic institute alone. So I think you can see a couple of slides illustrating the capabilities. As you can see that the various terms are given here, and we have been able to bring it to this level of IT3 grade with the parameters. So that means whatever we have set out at the beginning to produce certain components, being produced by the high precision grinding machines, we have been able to achieve it. And this data was collected after carrying out extensive trials on different components with the tooling and also fixturing. So as you see that this is basically starting from the requirements and then creating a framework and building a machine and proving the entire capability by considering the components from different industries has enabled us to transform this machine from one level to the next level, wherein you can see the improvements are quite substantial. And this has resulted into the transfer of technology after almost 1.5 years of the machine building and installation. So why I'm saying all this is where you can really bring in some transformational changes in manufacturing, which is the theme of this particular conference, and which we hope that many academic institutions and R&D units can learn some things from this presentation and then utilize this a framework or follow this framework. So at the end, I wanted to tell you that when we got this particular project sanctioned by the Principal Scientific Advisor's Office, so we were not quite sure of what we are going to do it. In the sense, is it that we are going to assess the status of the machine and then leave it there? Or are we going to identify the strengths and weaknesses and then keep it on in the report? Or are we going to utilize these technical pathways and framework for building the next generation machine? I think this is where the collaboration really helped us to bring different minds with different capability set and expertise to help the entire team And as you can see that the association like IMTMA and testing facilities available at CMTI. And there are advisors like Dr. Subbu from USA and the partner industry like Micromatic Grinding. All of them have played an important role in building this framework. I think I need to acknowledge all of them who have really supported. And as I said that Professor Mehta was chairing the committee and Mr. Neera Sinha was the convener. And of course, the members were drawn from the associations and industries, and of course from the R&D establishment, from IITs and R&D organizations. I think these are the ones which really drove us to the point that we need to build this as a unique, framework, and also make this machine into a next generation precision machine. I think, of course, a large number of students who have worked on this project without, any frustration and any fear. I think that I need to acknowledge them, and all of them are positioned very well in various universities abroad and organizations in India. I think the amount of knowledge that they have created and they have generated is the one which has really led us to the next level of building the advanced machine, the advanced manufacturing technology development center. I think I need to profusely thank all of them for their efforts and for their contributions. I think as you see today, we have this center at IITM Research Park, which is again the initiative of the Government of India. Mr. Mohan Ram has already mentioned in his a speech about the MHI's initiative in enhancing the competitiveness of capital goods sector. I think the industry partners have come forward to give their contribution without any hesitation, though we had some hiccups initially, but then finally we have been able to receive the contributions from them also. And I think what are we? Basically, we do a lot of research at the academic institutions and then leave it at the lab prototype level. That's what somebody said, the valley of death. And in fact, if you just remember, our chief guest also was mentioning about the TRL 4 to 6. You just leave it there and it goes into it. But then at this particular center, we wanted to transform this into a commercially viable product through a collaborative effort in a mission mode rather than leaving it at the laboratory level as a prototype. I think this is what I just wanted to convey. I think I took about 45 minutes to complete it. Thank you very much. Yeah, thank you, sir. Yeah, thank you very much. Yeah. Sir, yeah.
So, Dr. Ramesh Babu, can you see us?
Yes, sir. I think, can you see me? Yeah.
Very much so.
I'm sorry.
Neeraj Sinha, Mr. Mohan Ram, Dr. Mehta, we are all
Yes.
sitting here.
Recently found.
Yeah. Yes. Yes, sir. I think thank you very much for your support. But then I just wanted to personally, congratulate Professor Mehta ji and Mr. Mohan Ram. But then, can you see me?
Yes, we can see you.
Yeah, I think it was unexpected. Even on Saturday, I told Prabhu Raja I will come. And in fact, I spoke to Professor Mehta ji and also Mr. Mohan Ram that I'll definitely come. But then this was most unexpected, which took place on Sunday. So I thought I'll just keep, for some more time to carry on some more rituals here. Okay.
There's a question on the screen.
Yeah.
Chat box, call it the
Chat box.
There is a question in the chat box, Dr. Mehta. Can you see it?
Yeah.
It's
Yeah.
only for
Yeah, we can tell.
But you can see it.
Yeah, I think they wanted the delegates to post their questions in the chat box.
There is one already.
I think we cannot read it. We have to read it.
Someone should read it. Doctor, you read it.
Okay, let me read this question. If you are not able to see it on the screen, it is from Suresh T. The question is, could you share us the productivity improvement which has been achieved compared to existing machines with approximate output figures or numbers? He wants to know what is the productivity improvement you have achieved on this redesign high precision machine.
You see, we are looking at the high precision. Let me share my thoughts on it. I think what we have aimed in this project was on the high precision machine tool. I think whatever machine which was available before we took up this project was giving certain precision level. I think I have clearly shown in the table. I think it was giving more than 5 microns, and more than 3 microns. But we have brought it down to 1 micron and less than 3 microns. I think our main focus was on the precision improvement, making the machine into a high precision machine. The productivity, maybe by means of using certain elements, we expect that the machine building time can be brought down. And by using the various models such as the tolerance stack-up and tolerance synthesis models, we felt that the manufacturing professionals need not unduly assign the tolerances, but they can do it in a scientific way. That's where all these efforts will really help the manufacturing fraternity.
Thank you.
Thank you.
Are there any other questions anyone wants to ask Dr. Kaila? There are no other questions. Can we close the session?
Yes, sir. I think I'm fine with it because I've been asked to I think stop it at sometime 40 minutes. So I've taken more than 40, so I thought it is enough.
Doesn't matter because you have presented a very, very interesting case study. On behalf of all the participants, I would like to thank you for this. And it clearly brings out a very systematic approach to precision machine tool design, where you segment the total work into 3 or 4 major blocks and attack each one from the point of view of analysis, design, and manufacture. I think you did a lot of data gathering during manufacture on the errors of components and then how they stack up. Then brought out certain rules on how to minimize this. So this, whatever principles you have given in this can be applied to any other machine tool as well.
Yes.
And your work should be of great importance and interest to machine tool builders as they go from precision level of 5 microns to 2 microns and finer, not only on grinding machines, but also on machining centers, turning centers, and others. So I'd like to thank you on behalf of all the participants here, Professor Ramesh Babu, and thank you very much for a very informative, highly technical and useful presentation.
Thank you very much, sir. Thank you. Thanks a lot. Bye-bye.
So Babu, can I make a point here?
Sure, sir.
It is very immense work that you have carried out. I feel that you are the most competent person to take up the writing of a book on machine tool design based on these modern concepts. Because the existing machine tool design books are all outdated, including mine.
Yes.
So maybe you can pool up your resources with other people who are working on these new concepts of machine tool design, like Professor B.V.M. Rao's team in IIT Delhi, for example.
Yes.
And with the support of IMTMA and the industry with which you have a very strong interaction base now, I think it's high time that you take the lead. And with the backing of AMTDC, for example, with you, it's high time that you, with the collaboration of these people, take up the writing of a book on machine tool design based on these concepts.
Yes, sir. Thank you. I think you also suggested some time ago, because of our other 11 projects which are eating away our time, most of the times, and then this COVID also has disturbed all our activities. I think we will actually look into it and then bring out all these the scientific as well as the engineering concepts into a monograph or something like that. I think if you remember that, I'll definitely consider this. Now I think we are coming back to normalcy, and hopefully with the completion of all the other projects also, the amount of knowledge that we have generated is going to be helpful for building this monograph.
This will be documented as a permanent document, which will be useful for the industry and students and researchers across this wide spectrum.
Sure, sir. Definitely we'll do that one, sir. Thank you. Thank you very much, sir, for your support.
Thank you. See you then.
Bye, sir. Thank you.